Welcome to On Chemistry. In this video, we are going to see very important organic concept, Wagner-Meerwein rearrangement. Without this, you cannot see any exams. It's a very important one. Stay tuned. What is inside this video? First, we will see what is rearrangement. Then, Wagner-Meerwein rearrangement with mechanism, stability of cation, and migrating group and its priority, mostly migrating ability. The most important thing is we are going to solve 5 important problems from various examination and 5 tricks for solving the problems. First, we will see what is rearrangement. The normal reactions obey normal chemistry. The normal reactions are addition, substitution, elimination, degradation, and polymerization. With normal chemistry, you can understand those reactions, but for rearrangement, you have to master the mechanism because the atom will rearrange, you will get completely new products. That's why most of the rearrangement reactions are with scientist name. It is very unique and very important. Let us see Wagner-Meerwein rearrangement. Wagner-Meerwein rearrangement is to create stable cation. So wherever the intermediate is cation, Wagner-Meerwein rearrangement is possible. Here I shown alkyl halide. Cation is forming. The cation is primary cation. It is less stable when compared to tertiary. So methyl group migrates. You have new cation which is tertiary, very stable, and you get the final product. Here methyl rearrange to get the stability of cation. That's why it is cationic rearrangement. The moving group is called migrating group. The migrating group can be methyl, methylene, or hydrogen. Most of the time alkyl halides or alcohols will be used. Catalyst could be cation promoting species, HCl, sulfuric acid, or any Lewis acid like AlCl3. Solvent should be polar since the intermediate is cation. Polar solvents promoted. The cation stability is more important here. So we will see exclusively cation stability. In normal chemistry, stable cation is tertiary, secondary and primary due to hyperconjugation or more alpha hydrogen. Tertiary is more stable. So the order could be tertiary, secondary, primary, then methyl. So in Wagner-Meerwein rearrangement, always stable cation forms. Then the question will be which will migrate. Since the intermediate is cation, electron stabilizing species will migrate. If you can say in another way, electron dense group migrates. Here I shown two different category. In R group, that is alkyl or aryl, migrating order will be H minus, pH minus and CH3 minus. Why? Because hydrogen is very small with negative charge, high dense, move first. In the case of substitution, the group with electron donating group migrate. Group with electron withdrawing group don't migrate. Benzene will be neutral here because there is no substitution. So the order will be electron donating group, then comes neutral hydrogen, then NO2 electron withdrawing group. The concept you have to learn here is electron stabilizing group migrates. Then we are moving into the very important section, questions. The first question is starting material is alcohol. You are using concentrated sulfuric acid. You should find what will be the final product. This is a typical Wagner-Meerwein rearrangement. Alcohol you are using, acid is there. Acid makes alcohol as a good leaving group as a water. So water leaves, you have cation formation. The formed cation is secondary cation. There are the chances for tertiary cation. For that hydride has to shift. So hydride shift, you have tertiary cation. Since you have stable cation, There is no other quenching pathway. So what really happens is hydrogen eliminates. You have alkene. So cation stability drives the Wagner-Meerwein rearrangement. Then the next question. Here you have benzene. Side chain you have alcohol. You are using HBr. You should find what will be the final product. Here alcohol is there. You are using HBr which is equal to HCl, that is acid. Acid makes alcohol as the good leaving group. So OH leaves. You have cation formation. The cation is secondary cation but near the benzene. Benzyl cation is more stable than secondary. Excess stability comes from the resonance. So hydride shift, rearrangement happen. You have cation near the benzene ring. Then counter ion bromine attacks. You have the final product. The concept you have to learn here is benzyl cation is more stable than secondary cation. Then the interesting example, cyclobutane ring. Side chain you have two methyl group and chloride. You are using methyl alcohol. You should find what will be the final product. Here you have methyl alcohol chloride. The chloride attached with tertiary carbon. So the elimination SN1 mechanism is possible. You have cation formation. Since cation form near the ring strain is more. Instead of cationic stability, ring expands. You have ring strain reduction. So another stability established. Instead of cationic stability, ring stability achieved. So priority here is strain reduction rather than cationic stability. Ring open, you have cation formation. If you redraw the ring nicely, you have 5-member ring with cation. The cation is secondary cation. So what really happened? It can become tertiary. So another rearrangement to create the cationic stability. So methyl group migrates. You have stable tertiary cation. Since there is no counterion, alkene will be formed. The alkene will be more substituted alkene, that is say subproducts form. The concept you have to learn here is if strain present in the system during rearrangement, always ring expand, reduce the strain. Then the next question. Here you have cyclohexanol. Second position you have cyclopropyl. Methyl at the fourth position. You are using acid. You should find what will be the final product. This will be the best example for rearrangement because starting material and product you could see lot of difference. First step will be here you have alcohol, acid you are using. First step will be alcohol removed as water. You have cation. Cation near the strainful ring. 3-member ring is so strainful. What really happens is ring expands. You have cation migration. Here methylene group migrates to create the stability. 3-member ring will become 4-member ring. If you redraw nicely, you can clearly see 4-member ring. Cation formed near the junction. Then counter ion chlorine quench the cation. You have the final product. Then the final example, you have spiral system, 4-member and 5-member ring with alcohol. You are using concentrated sulfuric acid. You should find what will be the final product. Here same mechanism. Starting material has alcohol. You are using the sulfuric acid. Acid remove the OH group as a water. You have cation formation. The cation near the strainful ring, 4-member ring, which is very strainful, try to expand. So it expands, become 5-member ring as well as form the tertiary cation. So cation also stable, ring also stable. That will be the correct pathway. If you redraw nicely, you have fused 5-member ring. There is no counter ion, so quenching pathway will be hydrogen elimination and alkene formation. The concept you have to learn here is In ring system, always expect the ring expansion and total skeletal change. Then we will summarize and learn the few tricks to remember. The migratory aptitude for the rearrangement is hydride ion, then phenyl, then methyl. Then electron dense species move first. So electron rich mean electron donating group system. Electron less dense mean electron withdrawing system. Then stable cation is cyclopropyl group with CH2. It is the most stable cation because of resonance-like behavior. Then ring strain. 3-member ring is more strainful. 4 is next comes, then 5, then 6. So always ring system try to form 6-member. So if there is any strain, it becomes 6-member. Finally, non-classical carbocation also possible. It is like cyclopropyl cation. It is very stable. It will also promote the Wagner-Meerwein rearrangement.